Hello.
Hello!
Hello, everybody. Welcome. I'm really excited to be here. I haven't been to Brazil in many years, so thank you for having me. I'm so happy to be here. Um, I guess already know this. I don't know. I put on a slide. My name is Aaron Patterson. You can find me online as Tenderlove. Um, Lately, I've been doing a lot of live streaming, so please join me on my live stream. Make sure to click the bell and subscribe. Don't forget to comment below. All of that. But basically, on my live stream, I do a lot of pair programming. So if there's anything that you want to learn about, usually I focus on Ruby internals or Rails internals. So if there's anything that any of you want me to do, please let me know. I'd be happy to do that. Or if you want to pair on stuff, let me know. Yeah, that's what I have been doing lately. I work for a company called Shopify. I am on the Ruby and Rails infrastructure team. We do Ruby and Rails stuff. I searched through before I was giving this presentation, I wanted to think back on my last visit to Brazil, and I searched through my photos, and I can only find one photo in my album of me, and it's this one from 2011. So I look a lot younger than 13 years younger. Yeah, if you. This is to say, so what I want to say is I lost all of my photos from the last time I was here in Brazil. So please, after this talk, come say hello to me and let's take photos and stuff so that I can have good memories. Today I'm going to talk about some Ruby implementation details, and I'm extremely nervous about this because I know that it's 6 p.m. and we're going to talk about some very deep stuff. So I apologize. I'll try to make it as entertaining as possible. But we're going to talk about performance improvements in Ruby 3.3. Specifically, we're going to talk about some data structures. We're going to look at binary trees, and then we're going to look at red-black trees. I'm so sorry. This is not a joke. I'm not doing a bit. We're actually going to do that. And then we're going to look at instance variables as well as object shapes, and we're going to try to understand what makes instance variables slow, and then we're going to try to speed them up. And I apologize, there's also going to be math in this presentation. But I promise it's not that hard. I was watching some presentations earlier about doing front-end stuff, and I cannot do that at all. It's way too hard for me. I promise to you this math will be easier than that. So the first thing we're going to talk about are data structures. And I want to talk about binary trees. We're going to talk about binary trees here. Binary tree is a very simple data structure. It looks like this. A binary tree is a type of tree where the child node on the left-hand side, the value is smaller than its parent node, and on the right-hand side, the value is larger than its parent node. And we can divide all of these up. So in this case, 3 is less than 5, so it's on the left of 5, and 7 is greater than 5, so it's on the right of 5. So you can see how we would kind of divide up this tree. So when we build a tree like this, we're gonna walk through building a tree. It starts out as empty, and then the first thing we'll do is say we'll insert the number 5. So we're just gonna build exactly the same tree we saw in the previous slide. We start off with 5, we insert that, and then we're gonna insert 3, and we say, well, 3 is less than 5, so it goes on the right. Then we're gonna insert 2. 2 is less than 3, so it goes on the left. So 2 is less than 3, so it goes on the left of 3. And then we insert 4. Well, 4 is less than 5, but it's greater than 3, so we have to put it on the right of 3. And we just repeat this process for all the rest of the numbers in the tree as we insert them. And then we end up with a tree like this. So we're going to do it in slow motion now. We're going to add one node in slow motion. We're going to add the number 9. So when we add the number 9, we have to check, okay, is 9 greater than 5? If it is, we have to go down to the right. And we have to do that check for every one of these nodes. So we have to check, is 9 greater than 7? Is 9 greater than 8? And finally, when we get down to the bottom one, we can insert the number 9 into the tree like that. So if we implement this in Ruby code, it's pretty easy. This is the Ruby code for implementing it. And the algorithm is quite easy. On the left, we have the implementation, and on the right, we're actually using it. And all we have to do is, depending on the value that we insert, we either recurse down the left or we recurse down the right, and we choose whether to create or recurse in these particular situations. I'm not sure what the flog and flay scores of this are, so might not be too dry. All right, yes. So searching is exactly the same, almost exactly the same as inserting, but we just return true or false depending on the value that's in the tree. So for example, here we want to check for the number 8. So we check, hey, is 5 8? No, it's not. And we recurse all the way down to the value 8. We return true because we found it in the tree. Now, let's say we're looking for the value 10. It doesn't exist in this tree, but we want to find it. We know that 5 is greater than 10, or 10 is greater than 5, so we have to go down the right side. And we keep recursing down the right side, looking for this number. And finally, we get to the end. There's no more nodes to iterate over us, so we must return false. So we know in this case that we're going to return false. Now, the algorithm for actually doing the search is very simple. It's right there on the right. All we have to do is just check if it's greater than or less than to figure out where we need to go in the tree, and then we do a comparison to see whether or not it's the right node, and that's it. Now, I want to talk about like the worst case for searching one of these. Like, what is the worst case, our worst performance case? We actually saw that with the number 10. The number 10 had to go all the way down to the bottom of that, all 4 of those nodes it had to look at. So we can say that our worst case performance for searching one of these trees is the depth of the tree. So we can say that's our worst case performance. But let's make it even worse. We have kind of a problem. What if we take a list of numbers and we insert them in order? So let's say we insert 1, 2, 3, 4, 5, 6, 7. We have to keep inserting down and to the right. So we actually just end up with a list like this. It's just a list. It's not really a tree so much. It just looks like a list. And if we search this list, it means that we're going to have to examine every single node every single time in order to find that value. So we can say that the performance of searching one of these trees is ON, where N is the number of items in the list. So ON is not good. N stands for not good. So speaking of binary trees, like, I feel like you might think, oh, well, you know, we don't always deal with ordered lists, but I actually think, especially in Rails applications, that ordered lists are not that uncommon. And if you're not dealing with an ordered list, it's actually very easy to get an ordered list. And that brings me to one of my favorite methods in Ruby that I think is underused, and I want all of you to start using this, and that is the bsearch method. This is a method on arrays that you can use, and we're going to do a quick example of using this method. The bsearch method it treats a sorted list as a binary tree. So if you have a list that's sorted, you can treat that list as if it was a binary tree, and you can find items in that list. So let's say, for example, we have some active record objects. We pull out a bunch of active record objects. Oh, there's a little line there. We have a list of them, and we want to find we have a list of posts, and we want to find, is one of these the post we want? So we're trying to search this list. Like, how do we tell if post is included in this list? So one solution might be, well, we'll do post.include, and then we'll check to see if it's in that list. But that might mean we have to go through every single element of the list trying to find that node, or trying to find that post. So maybe another option might be, hey, well, let's turn it into a hash table where the key to the hash table is our post ID, and then the value is the post itself. But this isn't actually any better than the include call, because we had to go through every single item in order to create the hash. So this isn't actually any better. And this is where the bsearch method comes in, and we can just say, hey, let's use bsearch on this ordered list and find our object. I went ahead and did a little benchmark of this. We're just going to compare include and bsearch, and that's because we know that putting it into a hash is going to be the same speed as doing include. Oh, by the way, putting it into a hash can be useful if you know that you're going to be searching it multiple times. So you kind of amortize the cost of putting it into that hash. But if you know it's only going to be like once or twice, maybe this is better. So here's our example. We're going to do bsearch versus include. We benchmark this, and if we run this code, we'll see that doing the include is about 30 times slower than doing the bsearch. And this shouldn't surprise anybody if you know about doing these types of log-n searches. If you used git bisect, for example, you've encountered using a binary search. And this is really just the power of like ON searches versus log-n searches. I told you we were going to do math. I'm really sorry. It's true. So the lesson to learn from this is, don't bother with include. Try using bsearch. All right. So back to our binary tree here. The performance is just way too bad for us to use. We're not going to use this. I was thinking about the performance of this, and I was like, okay, well, how many times have I actually used a binary tree in my code? Like, how many times have I written this code and actually used it? And I realized it's exactly 0 times. I've never used this. I've never used this before. But that's because of its poor performance characteristics. So how do we get better performance characteristics out of that? The only way we can do that is if we make sure that the tree is actually balanced. We need to make sure this tree is balanced. It's not one long array like we saw before. And that's where a red-black tree comes into play. And a red-black tree is just a binary tree, except that it knows how to balance itself. So when you insert nodes into the tree, it'll balance itself. So we're going to take that previous tree that we saw, and we're going to convert it into a red-black tree and see what it looks like. Looks just like this. Here's a red-black tree for the same set that we saw earlier. The red-black tree, though, has a few different rules in it. We're going to cover the rules for a red-black tree. So the first rule is, it's pretty obvious. All nodes are either red or black. We have 2 colors. But I need to say that. This is the rule. It's a simple rule. The next rule is that all leaf nodes are black. So all these ones that are nil at the end, those are all black. They're always black. Yes, jiggle the nil nodes. Yes, great. Okay, so rule 3 is that red nodes cannot have red children. So red nodes are not allowed to have red children, and you'll notice that here. All the red nodes have black-colored children. So the 4th rule is the most complicated rule, and I'm going to try and walk us through it very slowly, and that is that every path from a given node to a leaf passes through the same number of black nodes. This is pretty complicated, but we're gonna use some Keynote animations here to try and understand it. So let's say we start at the number 3. We're starting at 3 here, and we want to go down all the way to the left. We'll go down. Start at 3. We'll go through 2, and then we'll go down to nil. We passed through 2 black nodes on the way to the leaf node. Now let's say we go down the other side of this tree. Let's say we start at 3, and we want to go all the way down the right. We'll start at 3. We'll hit 7, then we'll hit 8, then 9, and then nil. And we'll see here we only passed through 2 black nodes. So this rule is true. Any path that we go through here, we must pass through the same number of black nodes. I'm going to add one more rule here, which is a bonus rule. That's because I like to code in hard mode. I am a Vim user, yes. The root node is always black. This is our bonus rule, and we're actually going to implement this here in this presentation. But I think we're going to do. I mean, how many of you have implemented a red-black tree? A few? All right, great. Hopefully, we're going to do it a little bit easier than what you have done. We're going to do an Okazaki-style functional red-black tree, and don't worry, it's very easy. Don't worry about it. Please check out his paper. It's a great paper about writing a red-black tree. I have put his intro to the paper here, and I want to read it because I think it's very funny. So the intro to the paper says, everybody learns about balanced search trees in their introductory computer science classes, but even the stout-hearted tremble at the thought of implementing such a beast. We present an algorithm for insertion into a red-black tree that any competent programmer should be able to implement in 15 minutes or less. And so I thought to myself, well, I don't know if I'm a competent programmer, but I can write a blog in 15 minutes. So So why not a red-black tree? And hopefully it'll be less than 15 minutes. We're gonna do it here now. All right, so we're going to start by implementing leaf nodes, and as I said, our first rule is that leaf nodes are always black. So we'll just create a class here, which is our leaf node. Its color is black, and we're going to use Ruby's pattern matching feature later on. I'm not going to discuss what it is, right? What we're going to use it for, but later on we're going to deconstruct these nodes using Ruby's pattern matching syntax. So this method lets us deconstruct the node, and we know that it's always black. It has no children and no value. So that's what that method does. Our leaf node is also, this is a functional data structure, meaning that we'll never mutate it. And what's very nice about that is it means that, we have an insert method here. We'll insert into our red-black tree. All that does is just call back out to the class method, insert passing itself in a value. This is just kind of a helper method to make our API look a little bit nicer. So our leaf is a singleton, and we're able to do that because, as I was saying, this is a functional data structure, meaning we will never mutate it. So it's okay for us to only ever have one instance of the leaf node in our system. We're never going to mutate this thing, so it's okay for it to be a singleton. And then anytime we create a new red-black tree, all we're going to do is we're just going to return this leaf node. That's it. This is all we're going to do. All right, so let's take a look at regular nodes. Regular nodes it's a very simple class. You should all be familiar with most of this stuff. So I just pointed out the deconstruct method here. All that does is it returns an array for use in pattern matching. It gives us back the color, the key, which is going to be our integer that we're storing, and then the left and the right values. That's it. And then we also have a nice little insert method here, which I guess is good. We have to match our leaf node. All right, so let's take a look at actually inserting a key. This is a little bit more complicated, but I'm going to break it down. The first thing we do is we're going to call into an auxiliary method, this insert aux. We're just going to call into that method. And then whatever node we get back from the auxiliary method, whatever it is, if it's red, we're going to convert it into a black node. So we're going to deconstruct it and convert it into a black node. And this is to take care of that one bonus rule that I said, which is our root is always black. All right, so our next thing, in the auxiliary function, all we do is we say, hey, if the tree is a leaf, if it's a leaf node, then we're just going to construct a new red node, and the red node will point at the key, which is the key in our, the number that we're inserting. And this is kind of weird, but we need it for our algorithm to work. All right, so let's walk through this. The first thing we do is we create a new red-black tree. All that does is it returns a leaf node. That's it. Then we want to insert the number 5. When we insert the number 5, we call the auxiliary method. The auxiliary method says, hey, we're inserting above a leaf node, so we're just going to return a new red node that points at the number 5. So we end up with a tree that looks like this on the right. So we have a red 5, and it points at 2 leaves. Now we return that, and then our insert method is like, oh, you gave me a red node, I'm going to convert it into a black node. And that's all it does. It returns back to us a black node that looks like this. So in the end, we end up with a tree that looks like this. The next thing we're going to do is we're going to insert a second key. We want to insert the number 3. So 3 is less than 5. That means that 3 needs to be on the left-hand side of 5. Oh, right. And if any of you start falling asleep, I'm going to push this mic forward until I wake you up. All right. So it needs to be on the left of 5. So we're not going to modify this code whatsoever. We're going to do the insert and see what happens. So the first thing we'll do is we'll call in to insert aux, and we're going to pass in the lower left value, which is our leaf. We're going to say, hey, we want to insert the number 3, and it's got to be on the lower left of 5. The current lower left of 5 is a leaf node, so please insert the number 3 there. What ends up happening here, in this case, the auxiliary function will just return a red node, and we'll end up with a tree that looks like this. That's it. Very simple. So we'll do one more. Oh, right. In this example here, we actually have 3 different versions of our red-black tree. The first one here is just our empty one that points at a leaf. Our second one is the one that points at this tree on the far right. And then the third one is that one in the middle right there. So we're going to do one more insert. We're going to insert the number 2, and we're not going to change the code at all. We're just going to insert it and see what happens. When we insert the number 2, we're going to say, well, 2 is less than 5. 2 is also less than 3, so we need to insert it on the left of 3. So we'll call insert aux with the leaf node. It just creates a new red node, as we've seen before, but then we end up with a tree that looks like this. Now, unfortunately, we have a problem. This is violating one of our rules. Rule number 2 says red nodes cannot have red children. So this is a problem. And this is where most of the issue of implementing a red-black tree comes in. We have to rebalance. So if any of you remember this from school, this is probably the really bad part. So what we have to do is we have to detect violations like this. We say, hey, I want to know about this pattern. I want to know about a black node that points at 2 red children like that. Now, the way that we'll resolve this is we're going to say, well, we know that this node here, it must be less than 5, and it must be greater than 3, so it's actually a valid child for the 5 node. And the way that we'll rebalance this is we'll kind of rotate the tree. I'm going to show you here in a nice Keynote animation that I worked very hard on. What we'll do is we'll disconnect those 2 nodes, then we'll rotate 5 below, and then we're going to reconnect the nodes like that. This is how we'll rebalance it. Then we'll color the number 2 black, and now we have a valid red-black tree. And we can actually put this into a more like generic form. So here's a more general form like this, where we don't actually care what those values are, A, B, C, and D. We don't care at all. All we care about are this Z, Y, and X. And the general form is we're just going to take those, rotate it, and then recolor X like that. That's it. And we can do all this very, very easily with Ruby's pattern matching. I'm going to show it to you right here. This is the pattern matching code. All we say is we're saying, hey, is the top node black? Also, is your left child red? And is its child red as well? And if that's true, then we're just going to go ahead and rotate the tree. And if that's not true, then we're going to return a new node. And that's it. That's all we have to do to resolve this. And it turns out there are only 4 different patterns we have to detect inside of our red-black tree, 4 different violations, and that's these different 4, all the combinations of red, left and right children. And what's really, really nice is that all of these can be rotated into the same tree, so we can rotate them all into a tree like this. And I've taken these trees and I broke them down into a table. The table looks like this. So this is kind of our table. We need to detect a black head, a red left, et cetera, and then we can just convert that straight into our Ruby pattern matching code like that. That's it. Now, all we need to do to finish this up is in our auxiliary method, we just say, hey, if the tree is empty, we're going to go ahead and make a new red node. If the number is smaller, we're going to go ahead and put it on the left. If the tree is bigger, then we're going to go ahead and put it on the right. And that's it. That's all of our code. And in fact, it's enough to fit on one slide if I turn it 90 degrees like this. Actually, there's one more thing to do. We've implemented our red-black tree, and I think we did it in like 5 minutes, or no, maybe 10 minutes. So I think we're doing better than the paper expected. But we have one more thing we need to do. We are able to make a red-black tree, but we're not able to search the red-black tree, so it doesn't do anything for us. So we'll add a search method here. It's really easy. All we have to do is in a leaf, if we ask the leaf if it contains the value, of course that's false. The node, all we need to do is return true if the keys are equal. Otherwise, we figure out if we need to recurse to the left or the right, and that's it. When we're using the red-black tree, it just looks exactly like this, and we can insert elements and check to see if elements exist. It works just like a set in Ruby. Now, what's really interesting, though, is each insert returns a brand new tree. It returns a brand new red-black tree. So you can do something like this. You can keep track of each version of this tree that we have. So we're actually getting a new version of the tree every time we call insert. But what's really, really cool about this data structure is that only rebalanced nodes are copied. We don't always copy new nodes. So these trees are able to share information between each other. So imagine if you had to do something like this with a set, for example, in Ruby. You might write some code like this where we say, hey, we're going to create a new set. We're going to add a value to the set. And every time we need to create a new version, we have to actually dupe the entire set, where we're able to accomplish the same thing with a red-black tree without copying the whole thing. So the advantages of this are that these different versions are able to share memory with each other. We get really fast inserts. We're able to insert at log n time, and we're able to do lookups at log n time. Now there's one little problem, like a little caveat that I'm going to bring up here, and that is that we can't really delete anything from the red-black tree. But let's not worry about that. That's fine. Let's forget about that. Though if you want to mess with this red-black tree, the code is right here. Go grab it, play with it. It's really fun to play with. So anyway, thinking back on this, I've used binary trees exactly 0 times. I've used red-black trees exactly once. And in fact, that's what this entire presentation is about. And I was going to call it that one time I used red-black trees to speed up instance variables in Ruby 3.3. But I figured that name was a little bit too long. So we're going to talk about instance variables now and how we use this data structure. So let's talk about object shapes and instance variables. And I want you to keep in mind as we're talking about this, I want you to keep in mind the advantages and disadvantages of the red-black tree we built. Namely, it's fast to insert, it's fast to look up, and we can have many different versions. However, we can't delete anything from it. So let's keep all those features in mind. So what are object shapes? Object shapes is just a way of mapping instance variables to indexes. So the way that we're going to talk about how object shapes work, we're going to look at it specifically, then we're going to talk about the bad parts. I'm not really going to tell you about the good parts. There are very good parts, and you should go watch other talks about that. But we're trying to speed them up, so we care about the bad parts here. So instance variables are actually stored in an array on the object, but we don't refer to instance variables by index. So for example, we have this node instance here. All of the instance variable values are stored in a list, but we don't refer to those instance variables by index, we use names. And we have to have some way of mapping those names to the index that we use in the array, and that is where object shapes come in. This is just a tree data structure. It's a very large tree data structure. It's also known as a shape tree. We call it a shape tree. And the way that we use it is that we have a tree that looks like this, where each node in the tree represents an ID, and each edge on the tree represents an instance variable name that we're using. So when we start out with a new objects always start at the very top. They start at 0, shape 0, and then each time we go through the tree, we change the shape of the object. So in this example, node starts out at 0. When we want to add the color instance variable, it goes to 1. Then when we add key, it goes to 2. Then when we add left, 3, and then right, 4. And that's basically all it is. Very simple like this. Now let's imagine that we had a second class. We have a node 2, but node 2 is a little bit different. It adds the instance variables in a different order. So what will happen in this case is we'll start off at shape 0 as usual. We'll set the color instance variable, and that'll go to shape 1. Then we'll set the key instance variable, that'll go to shape 2. But then when we want to set the right instance variable, we actually have to create a new edge in the tree. So we'll create a new node in the tree, and then we'll go down to shape 5. Then we'll create left, and we'll go down to shape 6. So the object on the right-hand side ends up at shape 6, whereas the object on the left-hand side ends up at shape 4. And the key to take away from this is that many objects and classes can share the same shape. We don't care what the class is. They can be, as long as the instance variables and the orders are the same, the order of the instance variables are the same. This tree cares about the instance variable name and what order that you set it in. That's all it cares about. So if I can give you one recommendation, it would be to set instance variables consistently in your code. It's a recommendation, not a rule, so please, you don't have to. Do whatever you want to. Do what you want. So I want to step through the process one more time, but I want to look at the process in a little bit more detail so that we can understand where the shortcomings are. So when this object is first created, we see it starts out at shape ID 0. Then the first thing we do is we add this color instance variable, and when we add that, we have to say, hey, was the color instance variable ever set before? And we're at shape 0, so obviously it hasn't been set. So we add a new shape. It's a new edge coming out like that. So we'll set color, and then we'll set the shape ID to 1 on that instance. Then the key instance variable, we want to set that, but we have to check, was the key instance variable ever set before? So we check in our shape tree, and we say, well, color is not key. That's not the same. And we go all the way up to 0. No, it hasn't been set before. So we'll create a new shape. We'll transition our object to shape number 2. Then we'll do the same thing for the left instance variable. Has this one ever been set before? And we have to say, well, is key left? No. Is key color, or is color left? No, they're different. So we'll add a new shape and create a new edge. And then we have to do the exact same thing with right, only this time we have to check, is right the same as left? Is it the same as key? Is it the same as color? We have to go all the way up to the top like this. We have to check each time whether or not this thing was set before. So the key thing to take away from this is that our instance variable index depends on that tree depth. So if we want to come up with the index, we just measure the height of the tree. But the other kind of problem is that before setting an instance variable, we have to check whether or not an instance variable has been defined before. So the bad news, maybe you will note from that checking, is that checking IVs is ON. It's n time, it's linear with respect to the depth of that tree. So even worse news is that our initialize is probably ON squared. Sorry, I told you there would be math. I gave you, it's fair warning. So imagine you have an initialize method like this, where we set a1, a2, a3, all the way through an. We'll end up with n squared number of checks on that tree, and that's not good. We don't like n squared. But the good news is that most objects don't have that many instance variables. They only have a few, so it's not that bad, right? Your objects don't have many instance variables, right? Right? Oh. Getting some nervous laughs here. Well, I have some better news for you. It's fine. It's okay. We have better news for you, and that's that we keep all of these values in inline caches. So we want to talk about those inline caches. Now, typically, we're going to go through this process again. We'll start out at instance variable 0. We'll go through exactly that same process we did before, but this time, we're going to set a cache in line. And this is just a cache that's in line with your code. You never see it, but we deal with it in the virtual machine. And this cache is just going to have a key, where the key is the shape that the object was. Then the value of the cache is the shape that we're going to go to, as well as the index that we're going to set. So we go through, the first time we run through this, we populate each of these inline caches with the shape, the next ID, and the instance variable index. Exactly the same process. But the second time we execute this code, we do a comparison. We say, well, what is the shape now? It's shape 0. Our key to the cache is the same. They match. So these two match. Our cache keys match, which means we don't need to consult the shape tree anymore. We just do our instance variable set. And as we go through each of these, it's fine. We keep getting cache hits. We don't need to look at this. We don't need to look at this shape tree. So maybe the first time we go through, it's expensive, but all subsequent times, we're getting really good cache hits. So it doesn't actually matter that much. So I also want to point out reads here. Reads are very similar. When we read an instance variable, we'll do exactly the same thing. We have to check, was color defined, and it'll go through the tree and check. And then we'll set a cache on that read. And the key to the cache, again, is just the shape ID. So the next read, when we check that, well, the shape matches, and we're good. So our cache hits are O1. It's very, very fast. But our cache misses are ON, and that's not good, as we have learned. So I want to talk about speeding up cache misses. And in order to talk about that, we need to know, when do cache misses occur? So here is one example. If you have a subclass can make the shapes different. So in this example, we have a subclass that sets an extra instance variable. And then every time we read, you'll see on the right-hand side, we're swapping reads. So we do a read on the first object. It misses, so we write the cache. Then we read again, it hits, so we're good. But then when we use the subclass, our subclass misses because its shape is different. But the second time is a cache hit. So we have that problem on read. We have a very similar problem on write. So this one's even worse here. We're saying in initialize, we set an instance variable, and then we call super. So you remember our ON squared before? We're always n squaring here, which is not great. Another example here is when we do lazily initialize instance variables. Nobody does this, right? Every time we do one of these, we can't necessarily predict which order these methods will get called in, so it may create a new shape there. And you'll see on the right-hand side, like, we start out with shape number 1, maybe we hit shape number 2, maybe 3, maybe 4, maybe 5. So this will mean that this B method or the A method will never get a cache hit in any of these calls. Now the good news is that in the larger scheme of things, like in the grand scheme of your code base, this is actually fairly rare. It's pretty rare. But I mean, we want to speed it up, right? Like we would like even these cases to be faster. So all these cases involve doing a linear search of our shape tree. We have to check like, hey, which one of these is color? Is color in this list? How do we find it? Wouldn't it be nice if we had like a hash table at each of these nodes where we could say like, hey, is color in this hash table? Then we don't have to check all the way up to the top. We can just check that hash table. But there's kind of a problem with this hash table. It's like, okay, well, we're repeating data all the way up the tree. So we have color inserted many times, we have key inserted many times, and left inserted many times. And you can see how we might be repeating information here a lot. So what kind of data structure might have fast lookups, decreased duplication, and all that? Like what might that be? Oh, that would be a functional red-black tree. Yay! We're going to use it. But I know many of you in the audience are saying, well, but you can't delete from that tree. How can you use this data structure? You can't delete anything from that tree. Well, I have news for you. Great news. Shapes are never deleted. So we don't even have to worry about this use case whatsoever. There's no requirement for deleting. So what we did in Ruby 3.3 is introduce an ancestor index, which is just this red-black tree here. The red-black tree composes this, creates these sets. So I came up with some benchmarks for measuring this, so we could take a look at the performance implications of this. Our benchmark looks like this. We're just going to set n instance variables on this object. And then we have a subclass that sets one more instance variable. And then we have a baseline benchmark, which just measures when we always have a cache hit, so we know what that looks like. And then we compare that when we always have a miss. So we're going to compare cache hits, always hit and always miss. And if we look on Ruby 3.2.2, this is how it looks. So along the x-axis is the number of instance variables we've set, and on the y-axis is how long it takes to run that benchmark. And you can see when there's a cache hit, it's linear. It's not linear, it's constant time. But when there's a miss, we have linear growth, and that's not great. We don't like that. But in Ruby 3.3.0, since we're using this red-black tree index, we can see like, yes, a cache miss is a little bit slower than a cache hit, but it's not linear, but it's very, very close to that. And since I gathered all this data, I decided to put them all on the same slide. So we can see here like Ruby 3.3 versus Ruby 3.2. Those cache hits, or the cache misses on Ruby 3.3, it's a little slower, but do we really care that much? Probably not really, especially compared to Ruby 3.2. So I decided, okay, let's change this again. We're going to change it to do, instead of reads, we're going to do writes. So we'll try writing and compare these. So it's exactly the same benchmark, and you can see our cache misses scale linearly again versus our cache hits, and we'll compare it to Ruby 3.3. Looks great. Like on Ruby 3.3, it's just a little bit of overhead, but we're basically the same, pretty good. Let's do one more example, memoization. This is one thing I'd like to benchmark. We looked at reading and writing, but both of those benchmarks measure the time for accessing and writing to an instance variable that's defined. We have another case where we have to check whether or not instance variables are defined. Probably some of you have written code similar to this, maybe? Yeah, okay. I wanted to test the defined method, and specifically I wanted to test the case where this instance variable is never defined. Like, what does that look like? So the idea of this benchmark is to replicate our initialize method. Because all the initialized instance variables, they're not defined at first, and we have to define them one at a time. So here is the benchmark for doing that. All we're doing is very similar to the previous ones, but instead of reading or writing, we're just checking for an instance variable, and it's never defined. We have one that always hits cache, and we have one that always misses cache. And I ran the benchmark for this, and then it looked like this on Ruby 3.2, which was not good. You can see that they both, it doesn't matter. Whether you hit cache or you miss cache, it doesn't matter. And it turns out because there is no cache on Ruby 3.2. So I have to tell you a story. I worked on this red-black tree cache, and I knew how it works. I know the performance, like the performance implications. And I thought to myself, okay, well, anytime we're doing like cache misses, we should be using this tree, so we're going to have really good performance. And I thought to myself, okay, great. I'm going to benchmark all these different cases, show off these really great numbers. Everybody will be impressed and happy. And then I tried this defined check, and this is what it looks like on Ruby 3.3. It's not good. And that is because it's not using the red-black tree. So now Ruby 3.4. This is what it looks like in Ruby 3.4. All right, so I want to I want to thank all of you for having me here give a talk, because if it weren't for this, this graph would not exist. We would still have slower methods. Still be slower. So thank you. The thing is, this is how we do open source development, all of us together. All right, let's wrap this up. So I've used binary trees 0 times. I've used red-black trees once, and this is a presentation about it. We talked about object shapes and instance variable performance, and the things I want you all to take away from this talk are, first off, ON is not good. Let's stick to log n when we can. In your applications, please use this method. It's a great method. You should use this for sure. Data structures are fun. I think they're fun even if you never use them. Because if you study these, one day you're going to come across a situation where you're like, hey, wait a minute. I never delete from this tree. Here's a data structure you never delete from. Oh, they go together. That's great. So you can use those when you come across those problems. But actually, one of the biggest things I want you all to take away is, like, I want you to write the code the way that you like. So I was mentioning some things in this presentation where you could, be more shape friendly, or do some things to make your code better, like faster with the VM. Don't do that. Write your code however you like, and then it's up to us as Ruby core developers and Rails core developers to make your code faster. We want you to live happy programmer lives doing whatever you want to. So please don't change your coding style based on this presentation. I've given you forbidden knowledge. Don't use this forbidden knowledge. So thank you once again for accepting this talk. If it weren't for all of you, Ruby would not be faster. Thank you so much for having me here. It's been a pleasure. I am so happy that I could come here and talk about Ruby 3.4. Obrigado.